And now moving on to the next report. No. Well, you can do this. We miss your report. Now we'll hear about the modern DSM creation algorithms in DPWs.
Слово «фотомод», между прочим, название.
There is no word PHOTOMOD in the title of my presentation, by the way. I'll try to be as brief as I can, since we are slightly behind the schedule. What I wanted to tell you is how various photogrammetric stations build DEMs and DSMs and what we're working on at the moment. Let's start off with terms and definitions. I'm not sure about English, but in Russian there is quite a mix-up involving terms and their definitions. In Russian, they use CML, that's a digital terrain model, and more rarely they use DSM, digital surface model sometimes. They use digital terrain model, but they imply something else. In fact, what we're talking about here is whether vegetation and houses are included in our heights. And sometimes there is a distinction between a regular grid or some cloud point, some point cloud. I will mostly talk about DSMs, even though I will sometimes use DMs, and we will presume that we are dealing with regular matrices. So how do we build a DEM? We take the left image and the right image. We need to fix the point on one image and find the relevant point on the other image, and then by the difference on the x-axis, difference in coordinates, we can calculate the height using the simplest formula. Historically, the initial methods of DEMs was the correlation method. I provided two formulas here. I will not bore you with trying to make any sense out of it. This is the correlation function. At the bottom, we have a difference between two intensities of the left and right images that can be brought to one brightness or contrast. So on the left side we have some pixels, on the right we look at the right side and we see whether we have some kind of extreme of a mathematical value. We can make things more complicated. We can assume that the red grid transforms into a rectangle. PHOTOMOD has an option called geometric correction during correlation. This is exactly the type of correlation that is provided at the bottom of the page. The method is quite old. It has clearly some advantages in that it doesn't have any memory requirements. It's quite fast. It has subpixel accuracy. You can read about 1/50th of a pixel, but today we heard about 1/3 of a pixel. 1/3 of a pixel, somebody told us, right? 1/4 or 1/5 or 1/10. So this much we can derive from this method, but it does have some shortcomings. If you're dealing with untextured background, I mean, if you have a gray background, there is no way you can match it with another gray background to compare them. If you have a clear horizontal line, the road, for example, this method works quite poorly, and it doesn't work well with other situations. But the key deficiency with this methodology is that it presupposes a certain type of smoothness. In other words, the left hand and the right hand images have to be more or less similar. And today we've seen examples where on one image we have one wall of the building, on the other we have the other wall of the building, and in such situations correlation doesn't work very well. Here we can see a strange set of mountains. In fact, it's the city, and if I launch the correlation using 50 centimeter ground sampling distance, we will have somewhat deformed and ugly looking hills which are removable from the picture. If we didn't deal with spaceborne imagery but aerial images, these hills would look somewhat nicer, less steep. How do photogrammetrists tackle with this problem, and mathematicians too? They decided let's try to come up with a global method. We will have energy that comes from two parts. One will be responsible for brightness on the left and right frames, and the other will be responsible for smoothness. If it's homogeneous, or heterogeneous, in case there is a change in smoothness. By introducing such penalties responsible for smoothness, a minimum of energy is used. If we consider such functionality, then the brightness in one image can affect height in a totally different section of the image, and these are NP complexity tasks, and sometimes such tasks are impossible to solve. Mathematicians came up with a good thing, but it's not of much use. It turned out there are several approaches here. The energy function can be replaced with something more simple. If I forget about interpixel connections, the picture will break down, and we will boil down to a method that is 20 years old, dynamic programming method. It's very straightforward, but it does not yield very reliable results. Another method is where we minimize energy approximately. We are dealing with graph cuts and belief propagation. We will approximate energy, but there is no warranty of any kind that belief propagation method will work well. We used the graph cuts method several years ago, I think 5 years ago, and I'm not sure we enjoyed using it. It's also quite cumbersome in terms of computing power. Recently, these three letters have been used a lot, SGM, or a simple tree method. Here the energy function is replaced by a simpler functional, where dynamic programming methods that I showed earlier allow you to find solutions of approximate functionality. This method is quite popular. Tomorrow we will have a dedicated report from Stuttgart on this method, and we will be exposed to a lot of outputs from this method. It's in active use, but it has a number of shortcomings. For example, there are memory requirements, quite significant. You won't have enough memory on your computer to compute to process larger images. Plus, you can only use a pair of images. What about multi-array applications when there is several pairs? There are constraints there as well. If it's not pure bipolarity, or if we're using space-based imagery, other difficulties arise. But other than that, this is an interesting method, and we've been keeping an eye on it for quite long now. What we focused on recently, and the results are quite close to SGM method there. This is a fairly unique approach. I believe that they use something at UltraMap, something similar to that, but I'm not so sure. The idea behind this technique is very simple. We take true orthophoto. If I build it using one image or the other image or a third image without hidden surfaces, by definition I should be able to produce the same orthophoto regardless of what image is used as the basis. So what we're working on is exactly we're building at the same time a true orthophoto and look for a surface. But this has to be type of surface so that there are no hidden surfaces. This method is fairly effective for accuracy and speed. We use the image pyramid. We use for detecting, we also detect hidden surfaces, but still additional filtering is necessary. But SGM requires the same kind of filtering. I hope in a year's time our users will be telling us about how wonderful this technology works with PHOTOMOD. So far, no screenshots on that. Thank you for your attention. Questions?
Да.
Maybe this is a fairly transparent idea, but I think that they used a regular local spatial corridor. But then, at the latest change, they compared orthophotos. When the next time I meet one of the developers, I'll ask that question.
Еще вопросы?
Any other questions?
You didn't mention the use of geometrical constraints like orientation constraints. Are you using it to reduce the solution
using geometric
space?
constraints, yes. We need to find the hidden surfaces that...
No, orientation constraints. Like collinearity condition, epipolar conditions.
Yes, we have already, all the images are already oriented, and we can make a resection from the Earth.
No, I mean using it in the matching process, those constraints, because they will reduce the solution space.
Maybe.
The number of blunders will be reduced, okay?
Maybe, yes.
No, you can prove it, not maybe.
Больше нет вопросов?
No other questions. Thank you very much.